Good. Let us start. Welcome everyone to this latest version of KDK, Curiosity During Quarantine, our online avatar of Kaapi with Kuriosity, since we can't offer you a copy these days, but we can still try to whet your curiosity. So we have continued this series, which we have been doing with the planetarium for the last 4 years or so. So we are continuing the partnership with the planetarium, and I'm very happy that today's topic is in some ways sort of a confluence of the things that are associated also with the planetarium and ICTS, because as many of you know, it was Professor Vishweshwara who started the planetarium in Bangalore, whose brainchild it was, and of course he was one of the pioneers in the gravitational in the study of black holes, whose signals were detected by the gravitational waves, and ICTS had the privilege of hosting him for when the first detection happened. ICTS itself has an active gravitational wave research group, which is part of the Indian LIGO initiative and the LIGO collaboration worldwide. And we have, in fact, Professor Ajit, who will introduce the speaker very shortly. I'm very thankful to Professor Archana Pai for agreeing to give this talk in this online format. And I'm sure many of you are looking forward to hearing from her about this exciting topic of black holes. So since the first detection, I think now the sort of floodgates have opened, and you'll hear a lot about that in Archana's talk, I'm sure. But before that, let me also say that ICTS has a number of other programs and other things also going on online. So you are welcome to try to look at our webpage and see various events. We are soon, actually, coincidentally, in collaboration with IIT Bombay, we are going to start distinguished series lectures in mathematics under the umbrella of the Mathematics Consortium of India, the TMC Distinguished Lecture Series, which will be jointly hosted by ICTS and IIT Bombay. And you please look at our website for announcements on that. We have a lot of other programs as well in a number of different areas. You can also watch some of our previous videos. So look at the YouTube channel ICTS Talks, and you will see a lot of interesting material, in particular on gravitational waves and so on. Also, if today's talk piques your curiosity. So with that, let me hand it over to Ajit, I think, is that the sequence? Yeah. So let me hand it over to Ajit to take this ahead.
Thank you, Rajesh, and good afternoon, everyone. It's a great pleasure to invite Professor Archana Pai from IIT Bombay, today's speaker. I'm particularly glad because Archana is a dear friend and a colleague of mine. Archana is an expert on gravitational wave data analysis. She has made a number of important contributions to the search for transient gravitational wave signals, such as those from coalescing binary black holes. She was one of the first people to think about ways of coherently combining data from multiple gravitational wave detectors to improve the sensitivity of searches for gravitational waves, thus sort of synthesizing a global size detector from data from multiple detectors, analogous to the techniques that radio astronomers currently use, for example, to image a black hole. Currently, her research group works on different aspects of gravitational wave astronomy and is one of the most important groups in the LIGO India scientific collaboration. They have also made significant contributions to LIGO discoveries, for example, in the detection of gravitational waves from massive binary black hole system that she is going to talk about today. Earlier, Archana did her PhD with Professor Sanjeev Dhurandhar, who is one of the father figures of gravitational wave science in India at IUCAA. And after a few years of postdoctoral experience in Europe, she came back to India almost a decade ago at ICTS with a faculty position. And 3 years ago, she moved to IIT Bombay, where she's working as a faculty member and leading an active research group. Her contributions are very well recognized. Archana was head of one of the first Max Planck partner groups at ICTS in collaboration with the Max Planck Institute in Potsdam, which is also called the Albert Einstein Institute. She has received the NRSN Award for Young Scientists that was instituted by the Indian Association for the Gravitational and General Relativity and Gravitation, the professional association of scientists working on gravity and cosmology, etc. in India. Without any further delay, let me invite today's Kuriosity during quarantine speaker, Professor Archana Pai. Archana.
Thank you very much, Ajit, for that kind introduction. And I'm very glad to be here today to talk to you all. Okay, so let's not delay it further and let's start with the topic of today's Kuriosity during quarantine session. So let me just begin. I hope I'm audible and my slides are clear. Okay, so let's begin. I'm going to tell you a little bit story. Right from, we start with the Galileo and we'll end up with the LIGO Virgo detections. Okay, so let's start with Galileo. In 16th century, I'm sure all of you know this famous demonstration which he did, and here I have a little cartoon. So here is Galileo, and then he's instructing the two fellows to drop two balls. One is a little bigger ball and the other one is a smaller ball of different material to drop from the Tower of Pisa. And what he observed was that both the balls reach the ground at the same time, irrespective of their masses as well as the material which they are made up of. Now this, of course, this experiment is very famous, and because of this experiment also this Leaning Tower of Pisa was very famous. This was done and repeated several times with the same observation. And this experiment actually lays the foundation of equivalence principle, which later on Einstein gave us a few centuries later. Okay, so let's move on to Newton. So all of you are very familiar with Isaac Newton, who gave us laws of motion. Also, he gave us law of gravity, which essentially states that gravity is an attractive force and the force is inversely proportional to the square of the distance and directly proportional to the product of the two masses. Of course, it could also explain the motion of the planets in our solar system. Now, in spite of both these experiments, I mean, all these laws given by the famous figures, there was still some incompleteness. And this incompleteness was sort of completed by Einstein in his famous theory of relativity in 20th century. So what he said is that the equivalence principle, which essentially says that if you have a massive object, then the massive object essentially deforms the space-time fabric, or you can treat it as a geometry around itself. And if you take a smaller object, so here I've sort of shown sun, and then this small object is Earth, and this small object is follows the motion depending upon this geometry. Okay, so the classic analogy which we give is, if you take, let's say, a big ball, okay, and if you place the big ball like this sun on the rubber sheet, okay, then just because of the placement of this ball, the sheet essentially deforms. And if you take a small ball and imagine that the surface is frictionless, okay, then the small ball will follow the trajectory based on the stretched surface of this formed because of this big ball. Okay, so this is captured in the equivalence principle, and it is essentially tells us that if you want to consider the motion of objects, okay, then it gets sort of mapped to the motion of object in the geometry. So the whole problem gets mapped to the geometrical problem. And what more it tells you, that of course if you have objects, so for example, if you have star, if you have a massive star, and if there is a there is a planetary system around that, okay, then depending upon the mass of the central object, okay, the geometry will change and the motion will follow according to what was given by Newton's law. Okay, if, let's say, if the gravity is very weak as felt by the planet, and if the velocities are small. So the Newton's law of gravity is essentially, you arrive at the Newton's law of gravity from Einstein's theory of relativity. If you have very weak gravity, which is what happens in our planets, in our planetary system, okay, and all the motions of the planets, they all follow the Kepler's law, all right, and Einstein's theory essentially gives you a complete description of gravity. Now, okay, so now if that is the case, then let's consider these two stars and imagine that these two stars are moving around each other in a, what we call it as a binary system. Okay, so they're bound to each other and they're bound by what we call it as a binary orbit. Okay, so I'm going to play a little video. So as they are bound and as they are moving, then the geometry around them is going to change depending upon the motion of this object, and as a result, based on their motion, okay, the whole geometry, the space-time fabric, will carry this information and it will propagate out in terms of the ripples as are shown here. So as they are moving, the geometry is changing, okay, it is capturing that information, and the waves, the ripples on this space-time fabric is what we call it as gravitational waves. This was the prediction of Einstein's general theory of relativity, and the ripples essentially propagate out from the source as are shown here. All right. So now we ask a question that, fine, if that is the case, then can we observe this? What are the properties of these ripples? Okay, and that is the whole story of the gravitational wave detection. So let's ask a question that according to Einstein's theory of relativity, okay, these ripples essentially they travel with speed of light. Okay, they travel with speed of light in the direction away from the source. Okay, then these waves are like transverse wave. That means if there are any changes, they are perpendicular to the direction of the source. Okay, and they radiate away all the asymmetries of the system. Okay, so we always draw analogy with, let's say, with, if you take a stone and drop on the surface of the pond, then the way the waves, the water waves propagate out from that drop is like that, the ripples you can imagine on this space-time fabric. Okay, so now I'm going to, so if these are the properties, then I will ask the next question, that what is the typical amplitude of this wave? Because if any wave essentially is characterized by the frequency and the amplitude. So the amplitude of this wave, I have written down, this is the only equation which I have put in this talk. Okay, I've tried to make this as pedagogical as I can. And here is for the students who might be attending this talk, I think it's something which they can do after this talk as a back of the envelope calculation. Okay, so I'm going to explain this equation to you. So h is nothing but the amplitude of gravitational waves. Okay, this h is proportional to 1 over r. It's inversely proportional to the distance to the source. So here r is the distance to the source. It is like any wave, for example. Okay, and for any wave, the amplitude always goes as 1 over r. Okay, it's the same thing which happens even for the electromagnetic wave. All right, and then you have this other terms here, which essentially captures the dynamics of the non-spherical motion of the overall dynamics. Okay, so here q is what we call it as a quadrupole moment. Physically, the quadrupole moment captures the sphericity of a system. Okay, so if you have a spherical object, then the quadrupole moment computed from the center is essentially 0. Okay, so for example, if you have a star which is like a sphere, and let's say if suddenly it shrinks to a point, then all through you will have quadrupole moment equal to 0, and as a result you will not get any gravitational waves. Okay, so here h is essentially proportional to the double derivative of the quadrupole moment. The dimensions of this quadrupole moment is m times the distance square. Okay, so you can do a back of the envelope calculation, and you can estimate what is the typical amplitude, right, of this gravitational waves. So I've done it for you here. So for example, if I take a rod, okay, so there is a rod here. Okay, so let's take a rod, and if I spin the rod, okay, so here I've shown a spinning rod. Let's associate some mass to this rod. Let's say 1000 kilo. It's a very solid, heavy rod. And let's take a length to be, let's say 10 meters, and I spin it with some 10 hertz. I keep this rod exactly at the antipodal point from me. Okay, so the distance is nothing but the diameter of the earth. Now, if you do this, and if I put in that formula which I gave you, then what I get is this h is a very small number. It is roughly 10 to the power minus 44. It's an extremely small number. Okay, this h is a dimensionless quantity, and I will tell you what this h really signifies when we talk about detections. Now let me do a same calculation with, let's say, a system which is an astrophysical system with, let's say, two neutron stars. So neutron star is a star which is roughly 1.5 times mass of our sun, and let's say it is packed in a city like Pune, maybe a radius of something like 10 kilometers. So it's a very dense star, and if you take these two neutron stars and I place them somewhere in our galaxy, okay, and I let them have a particular speed, let's say they are in the binary system, and I redo the whole calculation, then I get h, the amplitude, which is almost 23 orders of magnitude higher than what I got from the terrestrial source. So though the terrestrial sources also produce gravitational waves, just because of the amplitude that they produce is so less, it's very difficult to detect this gravitational waves. So we need to go to essentially to the astronomical sources, which are very compact, they are very massive, okay, and they would give gravitational waves which are detectable. All right. So now let's ask a question, how do we detect gravitational waves? So let's take a ring of particle, which I've shown here, okay? And imagine that the gravitational waves are incident on this ring of particle perpendicular right, to the plane of this part of this ring. Now, if that is the case, then the ring would oscillate the way I have shown here. Okay, so it will essentially, it will stretch and strain, okay, as shown in this figure. And this is the main effect which we try to capture when we construct the detectors. So for example, if you take a pipe, okay, so this is a cylinder, and imagine that this cylinder is made up of lots of such rings, and imagine the gravitational wave is passing by from, let's say, the axis of perpendicular along the direction of the axis of the cylinder, okay, then the whole cylinder will move as I have shown here. All right. So this is the effect of gravitational waves when it passes by the system. All right. And this is what is used when the detectors are constructed. Okay, so before we go to detectors and detections, okay, I would just try to give you a glimpse that there are a lot of astrophysical sources which produce gravitational waves. So for example, you have binary system, as I have just mentioned to you. You can have accreting system where you have a black hole at the center and it's trying to accrete some matter on it. Okay, that also produces gravitational waves. You can have you can get gravitational waves if you have a supernova explosion. Okay, when at the end stages of massive star, when it goes through the various stages, there is an explosion, and you can get burst of gravitational waves from there. You can also get gravitational waves, let's say if you have a pulsar, if you have a neutron star with magnetic field, and let's say it's rotating with some mountains on top of it, and then just because of this dynamics which I mentioned to you earlier, okay, it would radiate gravitational waves. So we have a large sources of gravitational waves. Here there is another interesting source. This is essentially if you have black holes at the centers of the galaxy, and if the galaxies merge, okay, the central black hole, the two black holes, they can form a binary system and they can emit gravitational waves. Okay, so we have a zoo of gravitational wave sources, and the goal is to essentially detect all of them very soon. Okay, and this is just a beginning. All right. So the first effort to detect gravitational waves was long back in 1960s. Basically, there was a professor in University of Maryland, Joseph Weber. So he decided to construct a metal bar. Okay, and the idea which he had is that if you have a passing by gravitational waves, then this metal bar would ring. Okay, it will get excited, and then you can essentially capture this excitement, okay, by by measuring this basically oscillation. Okay, and interestingly, he announced the detection in 1968 in a published article, and this was one of the initial sort of event which marked the beginning of gravitational waves, and there was a lot of excitement. People all over the world started building this resonant bar kind of detectors, and the whole field essentially began from this discovery. Later on, it turned out that the claim which he made was not from the astrophysical source, but it was due to the instrument itself. Subsequently, in again in 60s, end of 50s, Felix Pirani, okay, he came up with this fantastic idea that if you have light signal, you can use the light to measure the distance between the free test masses. So if you have test masses which are free, then you can use the light to measure the distance. And this was later on incorporated when the first proposal of LIGO was made, where Rainer Weiss in 1972, he essentially proposed this using laser interferometric detector to detect gravitational waves. He did the first feasibility study, because it's very important for any such detectors, because you have to, first of all, you need to have the masses to be, test masses to be free. Okay, so you need to assess various noises which would affect the instrument, and then you have to design the instrument in such a way that you can make the test masses free. All right. So, of course, now the proposal was accepted, and there was a long commissioning of initial detectors construction, and then the final, the science, it went through various phases. The science run was started in 2002, various science runs were taken, and finally the advanced detectors are now operational. Okay, so let's quickly look at what is the principle in which the laser interferometric detector operates. Okay, so there is a little video which I'm going to show you here. So this is the laser beam, and you can see that this is an interferometer, basic interferometer, where you have two mirrors. Okay, the light essentially reflects from two mirrors and combines, and then you measure the combined interference pattern. So here you have laser beam which is getting reflected from one mirror. It goes and combines with the other mirror's beam, and then you have this final interference pattern which you essentially record in the photodiode in terms of the intensity. Now, as the gravitational wave is incident, you can see this in this arrow, then you can see that this lengths of the two arms essentially alter, and as a result, the intensity pattern also starts showing that effect, and that is what you measure. So this was a very simple principle uh, on which these LIGO detectors are being constructed, and the goal is essentially to reach H, which is this strain which I talked about, the amplitude of a gravitational wave, which essentially translates into the strain. Okay, strain is delta L by L, right, of the order of 10 to the power minus 21. So now if you have L length, which is roughly 4 kilometers, then you are actually targeting delta L of the order of 10 to the power minus 18 meters. So which is 1 by 1000 of the size of the nucleus. So we are actually trying to measure those kind of uh, lengths. Here, actually, we are trying to measure the change in the path, which in turn translates into the phase difference. So the goal is to probe that kind of phase difference. All right. So these are the detectors, two detectors. One is Hanford, another is in Livingston, which is separated by 3000 kilometers. Okay. And of course, you need a long arm detector because as the longer is the arm, then you have higher is your delta L, which you need to probe, and hence it is better. Okay. Of course, there are lots of technological challenges here, which now they are all sort of successively overcome. Still, there are challenges to reach the design sensitivity. But essentially, in order to make these mirrors free, the mirrors has been they are suspended. There are multiple level suspensions. You have very high power laser beams are essentially used. Also, the whole thing is kept in the vacuum. You have very nice suspension fibers so that you don't have much of noise coming because of the thermal, because of the temperature gradient, etc. And as a result, the LIGO went through various stages of improvement, and now the advanced LIGO detectors are essentially an engineering and technological marvel. Just to summarize, these are the two interferometers with 4-kilometer vacuum chambers, 3000 kilometer apart. They're operating in unison, and by doing this, they're measuring the motion, which is roughly 10,000 times smaller than the atomic nucleus, caused due to the violent events in the universe located almost like millions and billions of the light years away. So it's a fantastic experimental achievement which has been made over years of research and development, of course. All right. So all this culminated into the fantastic discoveries which we are making day by day. The first discovery which happened, which was the path-breaking discovery, was on September 14, 2015. Both the detectors, we observed an event which was incoincident. Okay, so the event which happened, it looked like this. This is the famous plot of the first event. This is a time, this is a frequency, and what you see is essentially a sort of increasing, as the time increases, the frequency increases, and then you see the color essentially, or the brightness essentially captures the amplitude. Okay. So what is this? This is, it looks like that you have some kind of what we call it a chirp, where the frequency is increasing as the time is increasing, and then at some point it is reaching the maximum level and it is sort of damping down. All right. Okay. Now after a lot of investigation, uh, 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 it was concluded that this event came from, essentially it was the event of merger of two black holes. So the two black holes are shown here in binary orbit. So as they move in the binary orbit, they lose energy in gravitational waves. Okay. And because of which they come close to each other, they come too close to each other, and you can apply Kepler's law and the frequency increases. Okay. As it increases, and then finally it keeps on increasing, which is shown here, and then finally it merges, and then the final black hole which is formed, which sort of settles. Okay. That is what we call it as a ring down phase of this black hole, and where Professor Vishweshwara did his fundamental contribution. All right. So this is the signal which we received in the year 2015, and which marked the beginning of the gravitational wave era, gravitational wave astronomy era. So just to sort of give you the perspective, so here I have sort of, it's a cartoon of life on Earth. This event started when somewhere here, something like 1.3 billion billion years ago, when the cell life was just starting on Earth. And this event started at this epoch. Okay. Traveled the distance. Okay. And it was captured in the detectors in 2015. Okay. So this is the summary of the first event, which was the most remarkable. It was a collision of two black holes, one of 36 solar mass and 25 solar mass, which was located at 1.33 billion light years away. And the remnant black hole, remnant was it was a spinning black hole of the mass 62 solar mass. And in this merger, a massive, huge amount of energy was radiated away. Okay. So it was almost 3 times the mass of the sun. That much energy was emitted in a fraction of a second, and that translates into the peak power radiated into this huge amount. Just to give you a context. Okay. So if you calculate what is the power radiated by sun, then this is one, there are 23 zeros on one. Okay. So 10 to the power 23 times the power emitted by the sun. So it was a huge amount of energy which was radiated, and that was radiated in terms of gravitational waves, which gave rise to the signal which I just now showed you. Of course, this was a spectacular discovery. It was the first direct detection of gravitational waves. It was the first direct observation of stellar mass black holes in the binary system. It was also the first direct detection, evidence of the collision of black holes in a binary system. Okay. And this is the first time we observed black holes which are greater than 25 solar mass. So far I will detail you a bit later about which types of black holes which we have seen in the electromagnetic band. Of course, this spectacular discovery was recognized with the Nobel Prize in Physics in 2015 to Professor Rainer Weiss, Professor Barry Barish, and Professor Kip Thorne for their remarkable contribution to LIGO and the observation of gravitational waves. It was the fastest Nobel Prize which was conferred so far. All right. So now this was about the first event, and which I think became quite this discovery was quite sort of was acknowledged, and I think it made a lot of noise and sound, and everybody was aware of this sort of gravitational waves. And in true sense, the era of gravitational wave astronomy began. So now let's try to understand, when we talk about black holes, what is it that we knew before this discovery? Okay. So let's go back a bit and let's try to understand how the black holes are made. Okay. So here I have just shown you a little picture, and this is a picture of our sun. Okay. So our sun is is one of the very normal star. Okay, in our galaxy, and it is very stable. It has a stable configuration because currently there is a hydrogen fusion is happening, and it's getting converted into helium, because of which there is a pressure, and this pressure is getting balanced by gravity, and as a result it is in the stable configuration. Of course, this fuel is of finite amount. So at some point it is going to get consumed. And once the fuel gets consumed, then the star-like sun, it essentially goes through the era the phase which I have shown here. So essentially, a sun-like star, which is the star of roughly the mass of the sun. Okay, after, let's say, for our sun, currently the age of sun is 5 billion years, and after, so it's right at the middle of its age. So after 5 billion years, it will essentially consume all its fuel, and as a result it will have the helium core at the center. Okay, and then what will happen is, essentially, since as the fuel is exhausted, the central pressure, right, it starts dropping down. Okay, as a result, the gravity takes over, and the gravity starts basically shrinking the star. As it starts shrinking the star, then essentially the temperature inside starts rising, and it keeps on doing till the next level fusion can start, basically. Okay, so for example, if you have enough mass, then it can go rise to the helium fusion, and so on and so forth. That happens for the massive stars. But for sun, what is going to happen is, it is going to essentially go through something called as a red giant, where you will have a central helium might sort of start burning, but then there is a little shell, because of when it starts fusing, then it releases some energy. And when it releases energy, then the outer hydrogen shell, essentially, just because of it gets that energy, and it expands. Okay, and it goes to this red giant phase, where suddenly the shell essentially expands, it cools down, and it looks red. Okay, so this is a red giant phase, and then eventually, since sun does not have enough mass, okay, it's going to go to planetary nebula, and then it is going to essentially goes to white dwarf, where it's a quiescent phase, and it is going to just cool down. Now if you have stars which are more massive than sun, okay, so for example, in our universe, we have stars of, sun is very normal star. I mean, you have stars in the, what we call it, a main sequence star, where the stars are sitting, and just like sun, they are shining. Okay, so you have stars which are as big as maybe 200 times mass of the sun. Okay, now these stars, when you have, let's say, mass greater than 10 times mass of the sun, then after the hydrogen burning, okay, you have the helium core at the center, and then the gravity sort of takes over, and then it reaches, so when the temperature reaches the state where the helium can start fusing, that is the time the helium starts burning, and then the pressure again gets balanced. Okay, till the helium fuel is consumed, and this essentially keeps on going. Okay, till based on the mass and the available mass. So if you have enough mass, then it reaches up to, let's say, iron phase. Okay, iron is the most stable element. So you cannot fuse it further, because if you fuse it further, then it does not release energy. Okay. So now when it goes through this ion phase, then essentially there is nothing else which can support the central pressure, and as a result the gravity takes over. And depending upon what is the core temperature, size, ion core size, either the star goes through a neutron star or it goes through black hole. So it essentially goes to this red supergiant, which is pretty much like this red giant phase. And then essentially depending upon the core, okay, the core size, either it goes, if the core is quite heavy, then it collapses under gravity. Okay, it cannot take over, so it sort of collapses under gravity and it becomes black hole. Okay, all right. So it goes through this shock because there is something which sort of tries to hold it, and because when it tries to hold, then there is a shock which sort of pushes the whole thing out, and a large fraction of the mass gets sort of ejected out in the supernova. And then the final at the center, depending upon the core, either it goes to the neutron star where it's made up of either neutrons and protons, and then, or if it is more massive, then it goes, then the gravity takes over and it becomes black hole. So this is how the black holes are formed, and this is how the stellar mass black holes are formed. So when I talk about the stellar mass black hole, so before we go to stellar mass black hole, let me just tell you, when I say a black hole, just to recap, what is a black hole? So we think that the black holes are essentially the final end stages of a massive star. It's a very compact object, and just as Einstein has prescribed us, it essentially has extreme gravity, and so much that even light cannot escape from any black hole. Now, theoretically, it was predicted by Schwarzschild. The theoretical prediction was given by Schwarzschild in 1916. But the first black hole evidence was obtained by this source in Cygnus constellation. It's called as Cygnus X1 in X-ray astronomy. So this source was a source. So this is the artist impression of this source. So it was, you can imagine that there is a central black hole here, and it's a accreting system which is trying to accrete mass from the companion, and it is trying to accrete matter, and as a result, when in the accretion system there is a matter inflow, because of which essentially it produces the jet, okay, and which is what one can observe in using the X-ray telescopes. Okay, so there is some jet-like structure which is sort of which can be observed. All right. So now this is about black hole and what we sort of know about black holes. Okay, there are observationally there are three types of black holes, just based on the masses. Okay, what we call it as a stellar mass black holes. So the black holes with mass, let's say less than 100 solar mass. Okay, and typically the stellar mass black holes with X-ray observations, whatever has been observed so far, are between 5 to 25 solar mass. So before the first discovery of gravitational waves, nobody knew that there exist stellar mass black holes above 25 solar mass. Okay. Now, the story which I told you about how the stars are, or how the black holes are sort of formed, okay, this whole story of supernova explosion and subsequently forming black holes, okay. So this story becomes a little bit of unstable, because as you have more and more massive black holes, okay, or the massive stars, okay, then this whole scenario, many times it becomes unstable. And what people have shown, that theoretically you cannot form black holes, okay, by this collapsing mechanism between 65 solar mass to 135 solar mass. Okay, so again repeat. So number one, in the electromagnetic in electromagnetic observations, as far as the stellar mass is concerned, we have seen black holes only up to 25 solar mass. Okay, people who make black holes, okay, they have they have told us that you cannot form black holes between 65 to 135 solar mass. So that sort of gives us a gap, okay, in the black hole in the black hole sort of masses. Okay, we call it as a mass gap. Okay, all right. So now let's ask a question. Uh, so this is all about the stellar mass black holes. So now what about the very massive black holes? Yes, we all of us know that there are supermassive black holes, which is sitting at the centers of most of the galaxies. In fact, this year's Nobel Prize was announced uh, for the discovery of this supermassive compact object at the center of our galaxy. So I'll just take 2 minutes to just explain this so that we understand, right? So essentially, supermassive black holes are the black holes with masses something like million to billion times mass of the sun. Okay, and if you take a snapshot of our night sky, then this is the Sagittarius. It's like a teapot, and here is where we think our galactic center is. All right, and if this is where the galactic center is, then the central supermassive black hole is sitting there exactly. And what was done was essentially using the space sort of mission, right? So yeah, okay, right. So what was done was essentially, if you take bunch of stars around at the center of the galactic center, then the orbit of the stars was mapped. Okay, so this is one of the star, which is called S2, and the orbit of this star was mapped. Okay, and this was mapped for almost 16 years. And when this orbit was mapped, you can infer what is the central object. Okay, it was right. So, and this central object was the mass of the central object was estimated to something like 5 million times the mass of the sun, which falls in the realm of supermassive black hole. Okay, so Reinhard Genzel and Andrea Ghez received the Nobel Prize for this year in physics. Okay, for this discovery. I think it's a very spectacular thing to map the orbit of the star, which is very close to the galactic center, because you need that much of resolution to really get the map and to map it for a longer time and things like that. All right, so this is about the supermassive black holes. Now the question is, what about the black holes which fall in between the two? Okay, namely what we call it as intermediate mass black holes. Okay, so the intermediate mass black holes are the black holes with mass above 100 solar mass and with mass below the supermassive black holes mass. All right, so it's something like between 100 solar mass to, let's say, 100,000 solar masses. Okay, now there are various candidates of this intermediate mass black holes in X-ray astronomy. So the most promising candidate is the name is HLX-1, and it emits power almost like a million times that of our sun. Okay, and the estimated mass of this candidate is something like 100,000 solar mass. Okay, but this is all indirect, because the way it is done is you essentially compute what is the I mean, from the luminosity of this object, one can infer, okay, what must be sitting at the center. Okay, and so this is how it is done in the electromagnetics. For example, there have been candidates which emit very large X-ray luminosity. Okay, and you can see jets. Okay, so it appears that it's essentially it's a accreting system, and based on the luminosity you can estimate what must be the accretion rate, and based on that you can estimate what must be the central black hole which is trying to accrete the matter. Okay, so there have been indirect evidences of the intermediate mass black holes, but the first direct observation of the existence of black hole above 100 solar mass was obtained very recently. In fact, the announcement we made last month. Okay, and with the total with the final mass of 142 times the mass of the sun. Okay, so I will talk about this a bit later in this talk. All right. So now let's, after giving this brief summary about black holes, about the observations of black holes in our galaxy, now let's move to the binary black holes in the gravitational wave astronomy. So so far, along with the two LIGOs, there is a third detector which is also operational and doing the runs along with the LIGO detectors. This is called as a Virgo detector. So Virgo is the French-Italian collaboration. The detector is sitting in the famous city of Pisa, in the outskirts of Pisa, and it is of 3-kilometer arm length. Again, of the same, it operates along the same principle of Michelson interferometer, and all the three detectors have been working and essentially taking data. We have finished the third observing run of the LIGO Virgo detectors. All right. Now, besides that, there are a few more detectors. One is the Japanese detector, which will join the run very soon, the next run possibly, which is getting it's getting commissioned, and this thing operate in the operational. It's going to be coming in operation very soon. There is another detector which is in Germany. It's a smaller detector, and it is essentially used as a technology development for LIGO. And then we have the detector which is expected to come in next decade, which is the third LIGO detector in India. All right. So now with that, we will have a global network in place within 10 years. Okay. But for the moment, we have these three detectors, two LIGOs and the Virgo, which are operational and has taken the data. All right. So now with the third run, so we have taken the 3 observation run. The first, the big event, the first event happened in the first observation run. Okay, the third observation run was almost like 1 year long. Okay, we started last year on April 1st, and on that observation run, actually we have started making the public alerts. So once anybody can actually register and get the public alert of the runs. So just a moment. Okay, so this is sort of a summary of the public alert which we send out. And this is very useful because then if there are our friends from, let's say, optical astronomy, they can follow the event and they can see if there is something interesting, right? So it is, so it's sort of very nice, and anybody can see the public alert. So this is if anybody is interested, they can go to this website and see the LIGO public alerts. Now, in the third observing runs, we have seen many candidates, and the analysis is going on all these candidates. We have released only few events so far. Okay, but we expect that soon you will come to know about the latest development and the new candidates which we have seen in this observing runs. All right. Just to sort of give you the flavor of how frequently we see the events now. So this is a calendar. The third observing run started on 1st of April, And you can see all these crosses essentially indicate that the number of candidates we observed. I mean, in this month, in the July month, we observed almost like one candidate every 4 days. So, which essentially means that the gravitational wave astronomy is picking up at pretty much rapid pace. And very soon we are going to see lots of black holes, binary black holes, and all basically the compact stars, binary systems with compact stars, and maybe even more exotic objects. So far we have 50 plus candidate events, even more, and I hope you will hear about it very soon. All right, so now let's move on to little bit get a perspective of when we talk about black hole binary. Okay, so the black hole binary, as you realize, that it's essentially just two black holes in the binary system. All right, okay, so now we ask a question that okay, there are various questions. First is how these black hole binaries are formed. Okay, how many black hole binaries we have in our universe, for example. Okay, then what are these masses of these black hole binaries, right? So there are various questions about them. Okay, so now here let's ask a question that how these binaries are formed. Okay, so imagine, so let's look at this. So there are two sort of possibilities. Okay, I've sort of drawn a simple cartoon just to carry the message. Okay, so imagine that you have two stars, okay, which are what we call it as a main sequence star. Main sequence stars are stars which are essentially shining like sun. Okay, now if you have very massive stars, okay, then what happens is, as with time, okay, as with time, when they sort of go through their life cycle, okay, eventually here you can see that this star has gone through, let's say, supernova explosion, and then it has formed a black hole. Okay, so this star has become a black hole here. So now you have a black hole and the ordinary star. Subsequently, even this star would also finish all its fuel, okay, and as it finishes fuel, it can happen. I mean, it can go through, let's say, two kind of thing. It can happen that this star, okay, it has, let's say, it has a helium core, and then you have this, you know, the red giant, the phase which we were talking about, which sort of encompasses, because in that phase essentially there is a black hole here, so it will sort of encompass that phase because of the gravity of this, so it will form some kind of a common envelope. Okay, now there are two things can happen if the binary system, okay, gives out some energy to the common envelope. The envelope can sort of get ejected out, and then you can form a closed binary. Okay, and then eventually this star can become black hole, and then you have a merger. So this is how our black hole binary is formed here, right? But if, let's say, this this envelope is, let's say, not ejected, and here itself that they are very close, okay, then before the binary is formed, before this object has become a black hole, it can become that the all this mass of this star essentially gets gobbled up by this black hole. As a result, you will not form black hole binary system. Okay, so the formation of the black hole binary, it is not as trivial, because it has to basically fight with all these odds, and then the final black hole binary needs to form. Okay, that is number one. Now the second thing is, if the black holes are very far away from each other, okay, then it might take a long time for them to essentially merge. Okay, so, and if that time is so much, okay, that it may not even happen during, during the age of the universe. Okay, what we call it the Hubble time. And if it doesn't happen, then you will not observe them. Okay, but the fact that we are seeing black hole binary systems, right? So here, essentially, this channel of this channel of binary formation, we call it as isolated binary formation. Okay, where you have two stars, and eventually, after they sort of finish their life cycle, we have got this binary system. Now, there is another way of formation, which we call it as a binary. Imagine if you have this binary in a crowded environment. Okay, in a crowded environment means there are lots of objects around this. Such an environment exists. For example, in our galaxy, there are lots of globular clusters. Okay, where it's a cluster, there are lots of stars. Okay, densely packed, right? And if the binary is in such environment, then what happens is, then you don't need to have this channel, but it can happen that you have a black hole, one star has evolved and form a black hole, and then you have another star, and then the third body can interact because it's all is very crowded environment, and as a result, okay, this black hole can take place of this star. There is an exchange happens, okay, and you can have a binary system is formed. Okay, so now these are the two ways the black hole binary can form. Fine. Now the question is, okay, the question is the signature or the properties of this binary system, binary black hole systems are very different in these two different channels. Okay, so for example, if you have this two in this the first channel, when you have two black holes, okay, and when they, let's say, evolve after a long time, right? So imagine we start with these two black holes. Okay, the black hole also has spin. Okay, so they have some random spins, and imagine they evolve, they emit gravitational waves. Okay, now over the long time, okay, it will essentially radiate away all the asymmetries, and it will become aligned, what we call it as aligned. So you can have the, originally they were not aligned, and then with time, two black holes, they will be aligned, okay, with this orbital angular momentum. Okay, so this is a spin angular momentum, the black holes are spinning. The spin angular momentum will get aligned with this thing. Okay, so with the observations of the gravitational wave, the black hole binaries, which we have observed so far, looking at their spins, how the spins are, okay, the spin feature is captured in the signal which they emit, okay, one can infer how these black hole binaries must be formed, which you don't expect if the black holes are in the crowded environment, because then they can have any spin. All right, and there is no preferred sort of spin in such a crowded environment. Now the black holes which we have observed so far, they are all nearly equal mass system, except one or two, and most of them, they are like this, okay, except one system, right? So that essentially tells us about the formation channel. Of course, it's not something which is conclusive, because we need to have more observations to understand and conclude about the formation. Okay, so now what is it that we have seen so far? So this is essentially a zoo of all the black holes, as well as all the objects as far as the LIGO Virgo detections are concerned. So the story so far is, we have seen 12 binary black hole mergers, 2 binary neutron stars, and one neutron star black hole system. I'm not going to talk about the binary neutron star or neutron star black hole system here. So the 12 binary black hole systems, which are all shown in this triple sort of blue dots. Okay, so here all these purple dots, okay, they are the black holes observed in the electromagnetic band, primarily these black holes are the accreting systems, and all blue are the black holes observed by LIGO Virgo detectors. Here is what I sort of indicate. So first information is we have seen a new class, the black holes which are massive, which were not explored earlier, okay? And we have seen them in the binary system. So you can see that the number of black holes as observed over last 5 years, they have already surpassed the stellar mass black holes observed in the electromagnetic band. Okay, and of course this has posed new questions, namely if you look at the gap which I was talking about, the gap which is indicated when you form a black hole, which is between 50 solar mass, roughly 55 solar mass till let's say 130 solar mass. Okay, so this is a mass gap. And if you observe this event, which I will talk to you shortly, is the most massive event which we have seen and which we announced the discovery last month. And if you see this, especially this mass, which is a primary mass for this event, essentially falls exactly in this mass gap. The final event, the final merger, okay, it is it's roughly 142 solar mass, and it falls in the intermediate mass black hole regime. Okay, and this event makes it a very interesting detection because of its mass and the mass of both remnant as well as primary. All right. So what is this event? So it was essentially the shortest event which we observed on 21st May 2019. It is also most distant event, and it was the event made up of two black holes, one of 85 solar mass and another was 66 solar mass. This is a primary mass which falls exactly in the mass gap. Okay, and that poses questions as how this black hole must have been formed. Okay, because according to the recipe prescribed how the stellar mass black holes are formed, there is a mass gap, and you don't expect black holes in that mass gap. But we have seen this black hole, so that is an interesting question, and it also indicates that there are other ways of forming black holes. Possibly, maybe the black holes formed because of this, collision of smaller black holes in the crowded region, for example. And this has also given us the remnant black hole, which is above 100 solar mass. So far, there has been indication in the electromagnetic astronomy of intermediate mass black holes, which is about 1000 solar mass, but there was nothing so far observed between 100 and 1000 solar mass. And this is the first intermediate mass black hole in this region. Okay, so that makes this event very interesting, besides the fact that it is also the most massive event observed so far. All right, so I think I will take another 2 to 3 minutes. What's the, Ajit, can you remind me?
Sure, yes.
Yeah, okay, fine.
Yeah.
All right, so now with that, I will sort of move and give you a bigger picture. We are essentially We have just finished the third observing run of the LIGO Virgo detectors. This is what we call it as a frequency band of the detector. The frequency band is the frequency range in which you can detect a given signal. For the ground-based detectors like the LIGO detectors and Virgo detectors, this band falls in the audible frequency range. So it falls something like, between 20 hertz to a kilohertz, right? And this is where we are. Okay, this is this dashed line, which shows the advanced LIGO. We have not yet reached that level, but yeah, we should reach very close to that level. All right, and right, and now this essentially only captures signals or the compact binary mergers like binary black holes or neutron star black holes or two neutron stars when they are about to merge. So in their final stages of binary evolution, okay, that is the signal which we capture. All right. However, if besides this, there is a huge frequency band. If we explore that, then that will tell us more, not only just about, the mass, compact objects in a certain mass range. So for example, the LIGO Virgo, we expect that they sort of ride from, let's say, few solar masses to maybe total mass of roughly maybe 800 solar masses. Okay, up to that you can observe these systems. Okay, but now if you are interested in observing, let's say, mergers in of higher massive systems, then we need to go to lower frequency bands. Okay, and that's where the future mission, which is already on the table. This is the laser interferometric space antenna. It's called as LISA. Okay, it's a space mission of ESA and NASA, and the mission is that it's going to be a triangle which is following Earth's orbit, and essentially it's going to be an interferometric detector with lasers, but not really interferometer in a conventional way, but following the same principle in space, and that is going to look at very massive black hole binary systems. For example, it would look at intermediate mass black hole binaries. It would look at supermassive black hole binaries. For example, the LISA curve is here. So this is the frequency band of LISA. Okay, so the range of frequencies it would look at is something like in the millihertz, starting from millihertz to maybe 1 hertz or something like that. And it would look at more exotic events, and that is interesting, of course. And there is a future third generation underground detector, which is the Einstein telescope here, which you can see in the black curve here, which will probe our universe even much more deeper. Okay, and it will see even more stronger sources. So besides that, there are other missions planned, which is this BBO mission. There are also other alternatives, like you use the pulsars. Okay, the pulsars which provide sort of a natural detectors. Okay, so you can treat, let's say, the pulsar and the earth to be like an arm, a single arm, and then you can use many pulsars and take basically the passing gravitational wave will imprint the signature in the pulsar signal which you receive, and you use that to essentially try to probe what is a gravitational wave source. So there are lots of interesting things, and with that we expect to sort of cover the frequency band of roughly 12 orders of magnitude. And in true sense, it will be it will be like a gravitational wave astronomy spanning a wide frequency band. All right. And with that, we expect, of course, to answer lots of questions. For example, I mean, the questions like how is what is the population of black holes, how they are distributed, what are the formation channels of binaries, of course, also how the intermediate mass black holes are formed. It is believed that the supermassive black holes are formed by sort of having hierarchical mergers of intermediate mass black holes. So the question is, maybe we can find some, shine light on those questions. And we expect many more things to sort of unravel with as the gravitational wave astronomy full-fledged when it sort of grows into like electromagnetic astronomy in a decade or so. Okay, so with that, I will stop here. Okay, I have put some links here for those who are interested, especially students, to play with some data, for example. So we as community, we always maintain the open science page of gravitational waves, so where you will find more details about the detections. We also pull out the science summaries of all the detections. Okay, we also release the data. There are some small Python codes which you can play with. There are lots of lectures and videos and tutorials which students can play with. So I urge you to explore this material. Also, there are some games. So for example, this is a quite interesting game which you can play with the headphones on. So you can essentially put on your headphones and then you can listen to the signal, and then you will be made hear to the noise, the signal embedded in the noise, and then you need to sort of identify which data contains the signal. So I mean, there are some interesting things which I hope all of you will be able to appreciate, I mean, enjoy. And please stay tuned. Goodbye. So I think if there are any questions, I think Ajit will.
Yeah, thank you very much, Archana, for this
okay.
wonderful talk. We do have a lot of questions, and if you have questions, please do type them in the chat box. I can select them and ask them to Archana in some group way. So meanwhile, the listeners type questions. I can already ask some questions that are already been typed. So one is, you have mentioned that there are many sources of gravitational waves. So how do we distinguish that from, which source is coming from?
From where the source is coming from?
No. So what kind of sources are producing the gravitational waves?
Okay, fine. Yeah, so essentially, so if you have seen what I discussed just now, right, that the binary black hole, it has a very particular, if you take, let's say, binary system, right, binary system with compact object, neutron star black holes, okay, then it has a very particular signature. So the signature is you have the two objects which are inspiraling, right? So they go through this inspiral phase, okay, where they are essentially in a binary orbit, and the orbit is shrinking, and then the frequency is increasing, and as it comes very close to each other, right, it continues, and then finally they merge and then ring down. So this is what we call it as a binary chirp. It has this signature of a chirpy signature, where you have frequency increasing and then you have this ring down. Okay, so this is generally sort of detected using what we call it as match filter searches. Okay, where simply put, match filter essentially you do a phase matching. So so for example, theoretically, if I give let's say a black hole system of 10 solar mass, for example, then some spins, then we know from general relativity what should be the waveform. Okay, and then we essentially have the whole sort of templates or whole list of waveforms, just varying different masses and spins and things like that. Okay, and then we do cross correlation. So we correlate this filters with the data, and then we essentially see which one matches. Okay, so this is a phase matching, some kind of a pattern matching, but in a in the time domain. Okay, uh, that is what we do for this signal, this type of signal. Now, if you look at, let's say, a signal, for example, from supernova explosion, for example. Okay, now the supernova explosion, the typical time scale is basically a millisecond duration. So it's like a burst. And what you expect is, you expect that the signal will be like a burst. Okay, right? So for that, we don't use this match filter thing, because we don't know what kind of the signal, because it's such a short duration. Okay, and what we need to know is just to capture the power. So for that, we use this, the search is essentially based on just something which can capture the power. Okay, and it is essentially based on the time frequency map. Okay, so you make a time frequency representation, and then you have an algorithm which can capture the power and things like that. Okay, so based on the signal, we have different methods to detect the signal, because this signal is very weak and it is deeply buried in the noise. So we need to have special methods to detect the signals, and that gives us indication of what kind of signal it might be. Does that answer the question?
Yeah, thanks, Archana. So another question is it possible for multiple black holes to merge at once, and how would it be inferred?
Okay, fine. So, okay, so so two things. One is, as the detectors improve their sensitivity, okay, you see much deeper in the universe. Okay, now as you see much deeper, then your chance of seeing more black holes at the same time increases. Okay, so far we have not reached that level. Okay, number one, we might reach very soon. Okay, now if that happens, then how do you essentially figure it out? Okay, so there are various ways. One is, even if multiple black holes merge, okay, if they come from different parts of the sky, then using multiple detectors, okay, we can identify from which patch of the sky the signal has come. Okay, so if our detectors, so what we expect is, in future, right, we will have improved detectors, and we will have a network of detectors by which our sky localization, I mean the way you can localize the source in our sky, okay, that will improve. And even if you have, let's say, multiple detectors, multiple black holes, you should be able to distinguish. That is number one. The second thing is, as I just mentioned to you earlier, uh, the black hole binaries we essentially detect using this match filter search. So two different black hole binaries, unless they are of identical configuration, okay, they will have different signatures. So the signal duration will be different, the signal will be different, and as a result, the template or the filter which it will click will be different. Okay, so we use all this information in order to really identify and crystallize the source properties.
Thank you, Archana. So next is, how do we measure the speed of gravitational waves?
Okay, so the speed of gravitational waves was measured with the binary neutron star system. Okay, so I did not talk about that event at all. But since the question has come, maybe I should just mention. So there was a spectacular event. This was in 2017 event, August 2017. So this was essentially a merger of two neutron stars. And why I say spectacular, because when this event, when we received this in the gravitational wave window, then immediately 1.7 seconds later, it was observed as a gamma ray burst in the gamma ray in a Fermi satellite observation. And not only that, after that, I mean, there was a lot of excitement because this is the first time we have observed a joint event in the gravitational wave window and the electromagnetic window. And there was a huge campaign to follow this event. Almost like 70 telescopes were watching this event, and it was observed in subsequently in the X-ray and in radio and all the I mean, spanning the entire electromagnetic spectrum. So it was quite fascinating. And of course, there were a lot of things which were unraveled with this event. I mean, the main important thing was, for a long time, astronomers were not aware, I mean, did not know what is a progenitor, what is the cause of short gamma ray burst. Okay, so the short gamma ray burst is essentially it's a gamma ray burst event, but it's a very short duration, and they have observed many of such short duration gamma ray burst. But the source, I mean, what was the cause of that was not very clear, and this is the first time with this event it became clear that the compact neutron star binary merger could be the source of the short gamma. So this was one of the main puzzles in astronomy was addressed after the discovery of this binary neutron star event. Okay, now after this discovery, essentially the speed of, because now you know that knowing the of course, I think when they did the follow-up, also the galaxy was localized. Okay, and once the galaxy was localized, you know what is the distance to the source. Okay, so with the knowledge of the distance to the source, with the knowledge of that it occurred 1.7 seconds later, okay, you can put a bound on the gravitational wave speed, and using that it was confirmed that the gravitational waves indeed travel pretty close to the speed of light.
Thank you, Sacha. And another question is there a possibility of triple black holes to be formed?
Yes, I think, yes, of course, there is a possibility of triple black holes. I think the triple systems, yes.
But I guess the question is, then, do we expect the merger of?
That is a different, I mean, yeah. So what is the signature of that? Yeah, that is a different thing. I mean, when you form the triple system, I mean, well, it's a triple system. Yeah, I mean, what is the, I mean, the merger signature is, that is something which would be the most relevant thing for the gravitational wave window.
Right. Another question is, how do we measure the spin of a curved black hole? Because it was a Newman black hole, but we know that black holes astrophysical black holes don't have a lot of charge, so they are curved black holes. How do we measure the spin of a curved black hole?
Okay, fine. So I can tell you from the gravitational wave. So I did not talk much about the model as such. Okay, but essentially based on the spin. Okay, so in Einstein's GR, essentially you can obtain the gravitational wave emitted in the inspiral phase. Okay, which is a function of the masses and the spins of the component black holes. Now, when it goes and merges, okay, then there is a merger phase. The merger phase is essentially obtained using by basically putting the Einstein's equation in the computer, and you evolve it using the numerical codes. Okay, and then you get the merger phase, right? And then you have the what we call as the final black holes ring down phase, and that ring down essentially depends on the mass and the spin of the final black hole. Okay, so the spins essentially are the signature of the spins is already captured in the signal. Okay, so when we get the data, when the signal is already embedded in the data, okay, and when we try to estimate the properties, masses and spins, etc., then the recipe which we use for estimating the properties of the system as a whole, okay, essentially identifies that signal, okay, which matches the data the best. Okay, so using that we can infer what is the spins of the black hole, because the final waveform is essentially there is a stitching is done between the inspiral phase and the merger phase and the ring down phase. Okay, and that is used to get the properties, the final properties of the black hole, of the system.
Thanks, Archana. And there is, do we have a theoretical model for signatures of gravitational waves from supernovae?
There are some theoretical models. There are. I mean, these are basically based on the numerical simulations. There are, but there is no unique model as such. Okay, because it is, this involves a lot of complex physics. So, I mean, there are prospective waveforms, but there is nothing really like the thing. And since the waveforms are very short, right? So the signals are very short. As far as the gravitational wave window is concerned, what we are really interested in capturing the total power, signal power, okay? And which you can capture in any spectrogram or any, there are various time frequency based methods where you can map your signal in the time frequency domain, and you can capture the spectral features of the signal. So you don't really require very precise models to capture the supernova event.
Okay, thank you. Another interesting question is, does the appearance of black holes in the mass gap hint at any new physics?
So so I would say that so there are lots of, well, so I think there are a few things here. One is the mass gap itself. Okay, so this whole thing of the mass gap is itself is a new sort of possibilities, because this is all new sort of research. I mean, it's not something which is conclusive, because this lower mass gap, which I said is roughly 50 solar mass, it's also very, I mean, there is a big gap there. So it's something like 45 solar mass to 65 solar mass. Okay, and that depends on various factors, right? And then there are new studies which are sort of indicating that there might be this mass gap also can vary with reaction rates and other things. So currently, even within astrophysicists, the mass gap, what is the, I mean, though we say that okay, this is the mass gap, it is not the exact position of the mass gap is not really fixed. So that's number one. The second thing is let's assume that there is this mass gap. Okay, then of course the fact that our primary solar mass is 85 solar mass essentially sits deep inside the mass gap. Okay, it does indicate that possibly it is formed not by the conventional stellar mass core collapse scenario, but it might be formed by some alternative, maybe hierarchical mergers and things like that. But I would say that I think we need to observe many such systems, and currently our detectors are sensitive in this mass range, and I think more observations, we should be able to get more conclusive answer to this other possibility.
Thank you. There are a bunch of questions on supermassive black holes. I will club them. One is how supermassive black holes are formed. Secondly, why are they at the center of galaxies? And third, can a lone supermassive black hole produce gravitational waves just due to its spin?
Okay. Just due to its spin. So the black hole, just alone black hole can produce gravitational waves only if it is perturbed. Okay. If you have just alone, I mean, the standing supermassive black holes without really getting perturbed, it cannot produce gravitational waves. Okay. Now the question is about, what was the other question? Supermassive black hole, how they are formed.
Yeah, how are they formed? Why are they at the center of galaxies?
What is the second part?
Why are they at the center of galaxies?
Why are they at the center? Okay, so I mean, typically what happens is when you have, let's say, a collection of black holes, if you sort of imagine, okay, then the most massive system, right, via this interaction with other black holes, okay, finally it's essentially it goes and sinks at the center of the structure, okay, because it essentially sits at the center of this potential. It is a potential well, right, when you have more black holes. So any massive, so it essentially there is something called as a mass segregation happen. It segregates, it cleans up the stuff, it segregates the mass, and then finally it essentially goes at the center. Okay, it always sinks, the massive object always sinks at the center. Okay, that is number one. The second thing is how they are formed. So people do believe, I mean, this is just I mean, this is not something, this is an open question, that the supermassive black holes must have been formed by essentially hierarchical merger. I mean, there is a mergers of intermediate mass black holes, which they sort of they collide, and then successively you get this supermassive black holes which goes and sinks at the center. Okay, so that is what people, that is what the people believe, right? And a similar thing was also for the intermediate mass black holes, so that even the intermediate mass black holes must be forming in a very dense environment, like for example like globular cluster, right, where you have lots of black holes, and then you have this mergers. I mean, you have this compact binary system which interacts with the third black hole, and then depending upon the time scale and the dynamics, essentially a bigger black hole is formed, which again interacts, and so on and so forth. And unless it is not kicked out of the globular cluster, it stays inside, and then it keeps on happening, and then finally it goes and sinks at the center. So that is what is the whole story of this hierarchical merger scenario. And this is what I mean. Of course, it is not something which is confirmed, because we have so far we have not observed merging intermediate mass black holes. Okay, so I think with yeah, so I think let's wait. I'm sure I think soon we should be able to get a very clear answer, and I mean the clear observational evidence of how the supermassive black holes also, that they are also formed in the same way.
Thank you, Archana. There are some questions on more exotic physics also. One is, can we detect extra dimensions from gravitational waves? Secondly, could these black holes that we see, can they evaporate via Hawking radiation?
Mm-hmm. Yes, so I think maybe I will let Rajesh take these questions. I don't know if he's there. No, I think he's.
Yeah, no, Rajesh is not here.
Rajesh is not there. I think he's the right person to answer this, I guess. Right. So, yeah, regarding extra dimension, well, I think there are scope of putting constraints on some of these theories, right? Using, for example, uh, for example, the early universe, the gravitational waves coming from the early universe. We expect that with maybe the advanced detectors, maybe ET might be can be used to put constraints on these theories. So maybe I think using that you might be able to sort of put constraints on the theories uh, which have this possibility of extra dimensions. So that is one possibility. And regarding the black holes, I mean, the final black holes which are formed are like any other black hole. So if there is there is a evaporation, well, I mean, it is not different than any other black hole. So yeah, the question is, how do you really measure that? That I guess Ajit, you want to comment on that?
Yeah, maybe I can add that. One is that the Hawking radiation rate is
Yeah.
basically inversely proportional to a very large power of the mass of the black holes. This means that for any astrophysical black hole that we talk about, which are more massive than a solar mass, the Hawking radiation rate is completely negligible. So they would have practically no very little Hawking radiation. The temperature is in fact smaller than the CMB temperature. So that it's practically impossible to detect Hawking radiation from stellar mass black holes or black holes more massive than stellar mass black holes. But if there are some very light black holes, they would, less than the Earth mass or something, then they would produce some appreciable Hawking radiation. And currently people have used upper limits on things like gamma ray background to put upper limits on the abundance of such black holes, etc. So we'll take the second last question. One is, can you touch upon the LIGO correlated noise controversy in 2017? This is a long story, but if you want to take it, you can take it. If not, you can suggest some references.
Yeah, I think that would be good. Yeah, I think we can suggest some references. Yeah, that's true. I think that's
Yeah, so there are 3 publications have come out of one from the LIGO collaboration and 2 from independent groups, which
yes.
sort of successful, which have conclusively sort of responded to this controversy. So that's probably
yeah, I think that would be better. I think
yes.
yeah, because that's really a long story. Yeah, definitely.
Yeah. So maybe you can take the very last question. One is
maybe you can ask that person to write to me or something. I can send.
It seems that the person is familiar with the literature, but if not, you can look for the collaborations paper, which is called a primer on gravitational data analysis, LIGO data analysis, that came out last year from the collaboration. There are 2 independent groups also have written papers on this issue. Then maybe you could take the last question, Archana. Being an MSc, there are a couple of students have asked this question. Are there research opportunities for MSc students and undergraduate students in LIGO India, in the LIGO India science?
Yes, I mean there are. I mean, when you say LIGO India, do they mean experiments or do they mean?
I guess it's a general question.
Yeah. Okay. Yeah, there are. I mean, in fact, that's why I pointed them to this, especially for the students, for this open science page. There is also, I mean, there are people like myself, Ajit. I mean, we have. There are other institutes also which regularly take project students to do summer projects, or even the projects remotely. You can write to us, and then we can give you small projects, right, based on the open data. So that is quite possible. I think you can look into LIGO India page. I think that is the only up to date right now. I'm not keeping track of that, but
yeah, there's the Indigo web page
the
also has
Indigo, Indigo. Yeah, so there is another page which is gwindigo.org. Right? Yeah. So where you can find people or researchers in India who are basically doing. I mean, you will find a list, and then you can go to their web pages, and then you can contact them. And there are definitely possibilities of taking up research projects, definitely. But there might be. So what I suggest is, I think the nice thing is also to start with this open science page, because now there are lots of tutorials. So there is something which you can do by yourself, and then with that you can write to people, and then I think that would be right start, so that you can do it at leisure, and then you can contact people who can then guide you with more specific research projects.
Okay, thank you very much, Archana. I think this is a very good time to stop. It's been a long time. So thank you very much for giving this wonderful talk, and on behalf of all of us.
Yes.
And thanks to all of you for attending this also.
Yes.
So take care and keep well, and bye-bye.
Yeah, sure. Thanks a lot. Thanks a lot, Ajit, talking to you and talking to all of you. Right. And do write to us if you need any more questions, or if you have any questions, comments, stuff like that. Right. Goodbye.
Take care. Bye-bye.
Bye-bye.